Hello guys, in this video we're going to cover, it's like a continuation of pure substances. It's part of a playlist. So we're going to cover the effect of circulation temperature and circulation pressure on cooking. We're going to look at pressure cooker, that stuff. So, it's sort of an animated video, it's a study video. So, you know, it's a video where you take notes and you understand a concept. So, yeah, let's go on. And we're viewing it in the perception of engineering thermodynamics. Okay, so from table A4, saturated water temperature table. So yeah, these tables for someone who's doing thermodynamics, you must be convenient and use with them. And then all over this whole playlist, we have used them, and even the coming playlist, we're going to be using them. So from that table, it gives it plots temperature against pressure. Do I have it? Okay, I already included in the video, but in the previous video and the videos to come, I'll give you a sample of the table. But I think I could get you one. Let me scroll down. I think I have a sample of the table. For instance, this one here. Actually, it's right here. So this is what the temperature table looks like. Table A4. You know, there's temperature, saturated pressure, circulation pressure, saturated liquid, all that stuff, all them details. Okay. So let's get back to where we were. So from that table, once you have this pressure of 70.183 kilopascals as the circulation pressure, if you were boiling water, it was going to boil. It has to boil at 90 degrees Celsius. And if you have a pressure of 101.42 kilopascals, the water will boil at 100 degrees Celsius. So, and remember, circulation is like the boiling. So that means this is the circulation pressure, the pressure at which uh, the uh, the composition of substances, of a pure substance changes. When there's a phase change, that's the circulation. And you could see that this is the circulation pressure at this temperature, and this is the circulation pressure at this temperature. So when someone bees like water boils at 100 degrees Celsius and they stop there in physics and thermodynamics, and then logically, speaking and acting, that statement is not correct. The true statement is water boils at 100 degrees Celsius at 1 atmosphere, or at 101.42 kilopascals atmospheric pressure. Okay? Because water will still boil even at 70 degrees, at 90 degrees Celsius. And if the pressure is reduced so greatly to something like even 8.0, we would have water literally boiling at freezing point. You find it's like negative 2 degrees Celsius, but the water is boiling. So water there's no specific temperature at which water boils, but water boils at a temperature depending on the pressure in the atmosphere or in its surrounding. I hope you get that. So now let's look about cooking. Well, what is cooking? Logically, cooking involves chemical reactions, you know, denaturization of protein in foods, in meat and eggs. And this denaturization process depends on temperature and time. So now I want us to imagine a chef cooking at 3.1698 kilopascals. Well, that's a very, very, very low pressure. You know, the actual atmospheric pressure is 101.42 kilopascals, and now we have 3.169 kilopascals. That is like you're creating a vacuum and whatever in your kitchen, in your part. So it's theoretical. We're trying to understand it. Okay, you're not going to find a chef cooking at 3.169 kilopascals. No. Well, theoretically, you can do it because you're just gonna have to create an evacuated place. But it's quite expensive to create such a vacuum. But now, for the purposes of understanding, this is an educational video. So now we're going to assume that very low theoretical temperature, I mean pressure. So at this pressure from a table A4, in case you have a table you can try to relate, the saturation temperature is 25 degrees Celsius. That means at that point, water is able to vaporize. It's able to change phase from liquid to vapor at just 25 degrees. That's your body. Like our body is at 35 degrees. Is it 35? Yeah, I think we're 37. That's the normal body temperature. So now you're even under, just let yourself, you're not quite hot. But now you're cooking at a temperature that is even lower than the body temperature. So the water is even not warm, but it's vaporizing at such a temperature, at such a pressure, 3.1698 kilopascals. So if this chef was cooking, you know, this temperature is very small to fully denature protein and meat or the starchy foods like cassava, Just think of it. It's like placing, food in the under the sun, in the morning when that sunlight's just coming out. It's just warm, okay? Actually, 25 degrees Celsius even is not warm. It's below warm. So you don't expect food to cook, and that's exactly what happens when you cook at low pressures. So exactly. So here's the detailed conclusion of the observations, and scientifically what happens if for real, like the chef was to continue cooking at such a at such a pressure, 3.1698 kilopascals. The chef would have to take hours even to cook a simple dish like rice or spaghetti. Spaghetti takes around 6 minutes, 5 minutes. But if it was cooking at something like 3.1698 kilopascals, they would have to take like forever, like maybe 24 hours to cook, the spaghetti. When just a long time. And you would need a lot of water. Why would you need a lot of water? That's the tricky part. Remember, the water is vaporizing. That means even at a low temperature, water is becoming gas and it's going away. That means even because the water is going away, you're going to have bad food, you know, because before the food is being like fully denatured and cooked, for the water it's boiling and becoming gas and going away. It means for you to cook actually, you will need to use more water, and that's quite wasteful. And if uh similarly, if if a steamer was used, you know, so people have steaming at 3.1698 kilopascals. Remember, the circulation temperature is 25 degrees Celsius. Since the water is vaporizing at low temperature, the steam should be hot enough to do effective cooking. So even the steaming won't be effective. You will still take like forever to boil rice, to steam greens, and this stuff. Even in baking, due to the extremely low pressure, there is easier gas expansion. There's what do you think is pressure? Pressure is like in terms of thermodynamics, you would have like a container. How would you want to increase the pressure? Raise it highly. You would push the piston and you will reduce the volume to something very small. That's how you create a very high pressure. And once you reduce the volume, you're confining the gas to one place. But now, once you pull the piston back and you increase the volume, you're creating a low pressure. That means the gas can move around. The gas has many directions which you can move. The gas molecules. They can bombard, easily the stuff. So due to the low pressures in baking, there's easier gas expansion. That's food, especially bread, cakes. They're being baked will rise quickly. But despite of despite of the fact that they are rising so fast, you'll find the dough inside is not yet cooked. You have a full shaped cake. It's you know a donor pastry, but you gotta eat inside. You find very low, dough. Okay, the ingredients ain't not tart because it's very low temperature. So now, we said we are using this study video, and we're going to look at it in terms of physics, engineering, engineering thermodynamics. So now, after learning this theoretical condition, now you have applied as an engineer, and that's how we come about with a pressure cooker. So what's a pressure cooker? Literally, what a pressure cooker does is a pressure cooker, it helps to cook first. Something that you have to cook for like an hour. With a pressure cooker, you could cook it for like 30 minutes, 30, 25 minutes, 10 minutes. It reduces the cooking time by far like two great. And how does it work? In the beginning, a pressure cooker is a sealed vessel that controls the release of steam. So as the water that's being used to cook vaporizes, okay, the steam is trapped, and before I go any further, that's why for most of you who cook, if you've cooked before, once you're going to boil water or any food, you put it in a pan, put it on a gas, you light a match, and after doing that, you cover the food with another pan. Wow, you would have been doing maybe that randomly, like I have to cover my food so it doesn't get spoiled by the dirty air. But that's not the reason. The reason is you're trying to create a greater pressure to increase cooking. And there's a simple pressure cooker you're creating in your own room, at campus. So back to the pressure cooker. So once the steam is trapped, you know, if foods are cooked before, once you have a pan, there's food, and you cover it, and you take it off after some minutes, you're going to find there's some condensed water on the top of the pan that you've used on the lid, and that is where the physics comes in. That steam that has been trapped and condensed, its molecules are going to create a circulated pressure within that enclosure, within that system. This increases the this passes the it increases by about 15 psi. Psi is pounds per square inch, I think. Pounds per square inch. Yeah. So you don't have. I'd rather do the fact checking later. Should I do it now? Let me see. Oh, sorry, 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 sorry. I won't do that. Oh, I would love to do the fact checking, but it will interrupt the video. But in the next video, I'll clarify what PSI is. But I think it's pounds per square inch. You know. So that trapped steam is going to increase the saturated pressure within it by about 15 psi, which translates for 103.42 kilopascals above the atmospheric pressure. So the pressure within the inside it is increased by 15 psi. Now, once you add this 103.425 kilopascals to the atmospheric pressure, you're going to get something that is greater than or equal to 200 kilopascals. And that's a very, very, okay, it's not like very, very, but compared to the atmospheric pressure, is very high because atmospheric pressure is right here. You see, it's 101.325 And once you're boiling or cooking food with water at 100.01325 kilopascals, the water is going to boil at 99.97 degrees Celsius. That's why most people say water boils at 100 degrees Celsius, because for them, I don't care about our pressures. Okay? But now we have increased from here, we have passed all this to here. What do you notice? Now, the circulation pressure temperature is no longer 100, but it's 120.21. See the difference, the increment. So, what is going to happen? Now, cooking is going to be faster, same as steaming. And why? You increase the pressure, and now for you to boil a single unit of water to vaporize it, you need a temperature of 120.21. And you would ask yourself, then how are we cooking faster now? Now, this temperature, remember, our body temperature is around here, 37. So touch your body, you know. So now imagine a temperature of 120.21. This is hotter than even the hottest state you've ever been in. And now you're cooking food at such a temperature. If you were to press maybe your hand to a temperature of 120, it would melt. It would literally burn immediately. So now, because of such high temperature, there's easy denaturing of protein, within eggs, within meat, within beans, with the starch within cassava. It denatures instantly because of the high temperature. Even if someone maybe was a vampire and they were cooking you for dinner, I mean, it would be quite easy because once they press you in, you like literally start burning immediately because the temperature is too high. So theoretically, if somebody, maybe a chef, was to cook for at a temperature greater than this, maybe they go to something like 500 kilopascals. That means if maybe they were cooking like meat, if they pressed it water and they turned the adjusted the value in the pressure cooker to 500 kilopascals and the temperature resonance with that, it should cook within 0 microseconds because that's so much temperature. Okay, it's very hot, and steaming at such a pressure is also quite effective because it's the steam within the water is very, very, very hot. So I hope it made sense within this video. Sorry for the interruption about the PSI, but I hope it made sense. I hope you understood how a pressure cooker works and the logic behind it. So in the next video, for those who are doing thermodynamics, engineering thermodynamics, we're going to look at work examples. So make sure you check the video and check the video. Thank you. And yeah.